Assalamu alaikum guys. Today we are going to study the new chapter, that is the electron configuration under Unit 1 atomic structure. I am Najmunisha Asha. I came to explain you about what the new format of the electron configuration under atomic structure, how it shows the impact on that. Right. Let's we move on to the subject. The first we have to go through the content before you start any lesson study, right? So you have to know what is the major topics inside that. That's what is going to explain our knowledge of studies. Yes. So the first thing is introduction. Yes, guys, we have studied the electron configuration in your syllabus. So that is a simple manner we have studied what according to your electronic shells, right? Your atomic shell. That is a simple things, but here under your A level, we are not going to study according to that one. Yes, we have studied the different thing you can recall according to the principal quantum model. Yes, so you have the different knowledges about the principal quantum number. What are the different principal quantum numbers? So according to that, you have different principle to write a particular electron configuration of an atom. So let's move on to the principle of different electron configuration. The scientist has involved, then they have invented. This is how you have to write the electron configuration. The first principle that you are going to study is the outbound principle. The second one is the Pauli Exclusion principle. The third one is the Hans rule. The fourth one is the condensed electron configuration. So let's move on to the introduction now. Yes, guys, I already said you, this is not like your O level, right? We have studied the electron quantum model, right? So the principal quantum model, according to that, you have studied the different quantum numbers. Those are, you can say, is n is equals to principal quantum number, yes. And the second one is the L goes for the azimuthal quantum number. ML goes for the magnetic quantum number, and MS goes for the magnetic spin quantum number. According to that, we are going to write the electron configuration. Why? That is not like just your number of shell. We are going to speak about what the orbitals under subshells. We have studied the different orbitals. Can you all recall? Yes, guys. Those orbitals are S orbital, P orbital, D orbital. Yes, those orbitals are able to fill under different subshells. This is what we are going to study. Okay, under introduction, I'm going to explain about the word called degenerate. So what is mean by degenerate? Yes, in a many electron structure of an atom, okay, in a many electron atom, for the given value of n, yes, your principal quantum number, the energy of an orbital increases with increasing value of L. You should be very careful about that. As your number of the value of L is increasing, your energy of orbital also increasing. This is the simple manner. So go through this example, then you will understand what they are actually. The n is equals to 3. Think about that. If the n is equals to 3, yes, recall it. How can you find the L? The L is equals to, yes, let's use the text box. Yes, if n is equals to 3 now, you can say the L is equals to 0 to n minus 1. Right. So according to that, your L is equals to what? L is equals to 0. L is equals to 1. And L is equals to 2. And we know if L is equal to 0 now, What is that? That is s orbital. Yes. If L is equals to 1 now, that is p orbital. If L is equals to 2 means that is d orbital. And we know, right, according to this, okay, your E subshell, you know, under S orbital, you have only one subshell. Your P orbital, you're having two subshell. Sorry, three subshell. D orbital, you're having the 5 subshell. So this is means what? Your S orbital able to contain the maximum number of electrons. This is what we already studied here. 2 electrons. Your p orbital able to contain, yeah, 1 electron for 2 now. The 3 subshell is there, so that should be 6 electrons. Right? When you go for L is equals to 2, the D is equals to what? 5 subshell, therefore you can give that is as what? Okay. So this is what the simple thing that you can get if you know N is equals to 3. So guys, so look at these. They have given the energies in order. Yes, the 3s, 3p, 3d. The energy is increasing like that. Why? Your lowest energy is the highest stability. So 3s is the lowest one, and the 3d is the highest energy continuing one. Even though, right? What they are telling is your d is having the high energy, and you have the 5 subshell. Each subshell will contain the same energy what you had seen in your supercomputer. This is the simple one that they are showing us. So according to that, let's say clear all drawings. So this is what they are telling us. Orbitals with the same energy are said to be degenerated. Right? Okay. So are you all clear? So let's move on to the next clip. So now we are going to step into the principles. The first principle is the upbound principle. What the person upbound said. The filling of electron in an atom begins with the subshell lowest energy and continues upward according to the outbound principle. So we know who is the lowest person. Yes, that is S, and the highest one is D, F. It will go like that, right? So he said the filling of electrons, not like your O level, the filling of electrons according to your subshell, we are going to speak about what the lowest energy, that is the figure, it's clearly shown you. You have to write like this. This is your first shell will have the 1s. If it is n is equals to 2, you will have the 2s and 2p. If your n is equals to 3, you will have 3s, 3p, 3d. If you go for the n is equals to 4. Like this, guys, you can see, even though we are not talking about f, we are talking just about the f. So, guys, the start move along the arrows one by one. And this is the order of writing the electrons. So let's type and show you. And different part. Yes. Okay. So what should be the first? Yes, with me. So that should be what the 1s should be first. And you can see again, you have to start at here. And your second one should be here. Right? Again, it's going down. So the second one is what? It's 2s without any space. Right? Okay. And next, it has finished and it's starting from your arrow. It's 2p, 3s. Yes. And next, It's starting from the 3D. Okay, so this is how you have to write 3D, OP. I have missed 3 2P 3S 3P 4S, right? 3P 4S 3D 4P 5S, again 4D 5P 6S, 4D 5P 6S, then 4F 5D 4F 5D 6P 7S 5F 6D 7. This is the order. This is what should be the order that you are starting here. Right. So likewise, according to the above rule, he is stating starting from the lowest energy and moving to the highest energy. This is the order according to your electronic configuration, right? So let's move on to the next one. So you can simply the sequence of filling electron we have seen. So this is what that's the general order of energy level, and sub energy levels are shown below. So I already said that is the order. You can see the potential energy increasing like this. 1s, and you can see 2s, and again the 2p, 3s, 3p, and that is not the 4s is below than 3p. You have to know this order. This is very important. If you're unable to by heart, at least write like this and just go with that order and you will be familiar. Otherwise, you will miss something, right? So look at here, 3D, and next only the 3P is coming. And after 4P, you can see the 5S is here. And again, so not after 5S, you can see the 4D is visualized. So this is what the potential increasing order according to your section. So this is what about wants to explain you all. And the next one is the Pauli Exclusion principle. Okay, the order of energy levels in an atom. The Pauli Exclusion principle. He is the person. He said he postulates his name is the Wolfram Pauli. He said the number of electrons in an atom can have the same set of quantum number, that is N, L, Ml, and Ms. So let's see what he has said. So was postulated by the Wolfram Pauli. He said, since the no two electrons, right? The no two electrons in an atom can have the same set of four quantum numbers, N, L, Ml, and Ms. So any number of the electrons cannot have the same, right? Your two electrons can have the same quantum numbers. So what he is actually stating is the Pauli exclusion principle indicates that an orbital can hold a maximum of 2 electrons and they must have opposite spin. This is what we are studying under the magnetic spin quantum number. The electron always resembles in the opposite spins. So this is derived from the rule, the Pauli, the Wolfram Pauli, right? So this restriction allows to us index the electrons in an atom by giving their quantum number. Let's see what they are telling is. I already said you, right? When you take the different subshell. The subshell, right? We said the two atoms can have the oppositely. Maximum one orbital can have the two atoms, two electrons. The two electrons must be have the opposite spin. So when you take the S subshell, it always can have the one orbital that can hold the maximum 2 electrons. We already discussed about that. What about the next? Yes, that should be the P subshell. that will have the 3 orbitals can hold and the maximum of 6 electrons. Then go for what? Your D subshell, and which consists the 5 orbitals can hold a maximum of 10 electrons. So electrons are distributed among the various orbitals of an atom based on the relative energies of the orbital and the Pauli exclusion principle, and this distribution called electron configuration of it. Actually, Above explained to you what is the order of, what is the sequence of electron filling on, right? But Pauli has introduced the electron distributed. You know, the electrons are distributed among the various orbitals of the subshell, right? Based on the relative energies. Okay. So according to his, he has explained about what the electron configuration. The most stable electron configuration known as the ground state, right, is that in which the electrons are the lowest possible energy state. I already said why. So when we are speaking about the most stable, that should have what the lowest possible energy state, and it resembles the ground state. According to Pauli Exclusion, however, there can be only 2 electrons in a single orbital. So we have studied, right? So when you go for the S subshell, right, you will have according to the Pauli exclusion principle, however, there can be only 2 electrons in any single orbital, right? So according to the subshell, we are talking about the single orbitals will have only 2 electrons. That should be what the opposite directions. So that's the orbitals are filled in the order of increasing energy with no more than 2 electrons per orbital. So again and again, what the Pauli is insisting at. The orbital, the subshell will have on the maximum orbitals. According to one orbital, you have the maximum 2 electrons. That 2 electrons will show what? The opposite direction of the space. So example, okay, in a lithium atom, you know we have 3 electrons. That as what? One s orbital can accommodate 2 electrons. And the third one goes for the next lowest energy orbital, that's 2s. So you can see here, any electron configuration can be represented by writing the symbol for the occupied subshell and adding a subscript to the indicate the number of electrons. What they are telling is any symbol that you know. So we'll go for the lithium. I simply say the lithium is what? Right. So if you want to write the electron configuration for lithium, how can you write this? Right. The first thing is we have to write the lowest possible orbital, that is 1s, and what is the maximum number of electron that can be contributed, that should become as a subscript, that is 2. So s orbital can have only 2 electrons, right? Okay, the maximum it can hold only 2 electrons. What is your next lowest possible orbital is 2s. So these 2s can able to, we know the lithium is 3, therefore it will have 1. This is the pattern of writing the electron configuration. So this is what your subshell will represent, the subshell, and the subscript the number of electron number. Let me take it explains about that. Okay, so clear on this could be, say, your lithium is 1s2. Go for the sodium. Yes, 1s2, 2s2, 2p6, 3s1. How I do this? Okay. Again, we'll write and I'll show you. Okay. When you take your sodium, right, what is your electron configuration? Your atomic number of sodium is 11. So let's write the first lowest one according to the above rule. I will write here. So the lowest one is first is 1s. The maximum number that it can hold is 2. And second one is what? The 2s. The maximum that can hold is that is also, right? So the 4 has finished. Now we have another 7, right? And third one, you can have 2p6, right? The 10 is finished. We need another more one. So next lowest possible energy orbital is 3s. 3s1, right? Okay. So if you say carbon, what is the atomic number of carbon? 6. Shall we write the electron configuration? Yes, 1s2, then 2s2, the 4 is finished. Yes, another 4 is there. That should be, sorry, another 2 is there. That should be 2, 2. Count here, 2, 4, 6. The 6 is there. This is how you have to perform writing the electron configuration. So the electron configuration represented as orbital diagram. Each orbital is denoted by a box or circle. So usually we are using the box, and each electron by a half arrow or full arrow. What they are telling us. So if you want to speak about the orbital diagram, right? So you can use either box or circle, right? When you say 1s, take your lithium, it will have what? 1s2, 2s1. So you can do 2 box. So 1s1 we have fill one, another one. And again, if you're using the circle, opposite direction, and this is what we have to. Right. So let's go for the justification. Examples are given here. The half arrow or full arrow pointing up represents an electron with a positive spin magnetic quantum number, ms positive half. And the half full arrow pointing down represents an electron with a negative spin magnetic quantum number. There you can say ms is equals to minus half. So why we are using the opposite direction? We studied the magnetic quantum number. The electron can possess what? The upward is the positively charged, the downward is the negatively charged. That's why we are drawing these electrons upward and downward. This is very important, guys. Right? Then the electrons having the opposite spins are said to be paired when they are in the same orbital. Electrons having opposite spins are said to be paired when they have the same orbital. When you take the 1s, right, you should be very careful about that. You should be able to feel like this. Then only you have to spin to the, step into the second orbital to fill the electron. An unpaired electron is not accompanied by a partner of opposite spin. This is what the lithium experiences. Right. Now we go for Hans. The Hans, what he explains. The Hans said the degenerate having the same energy, right? Orbital, the lowest energy is attained when the number of electrons having the same spin is maximized. So he is saying, like, he is speaking about the degenerate orbitals. And the lowest orbitals are dying when the number of electrons having the same spin, that should be maximized. This means the electrons occupy orbitals singly to the maximum extent. If you take the 2p, if you take p orbital, you can have the 3p subshell, you can have the 3 orbitals. So the maximum number of the electron can have the single field. Then only it's able to parallel field, right? So here he said the electrons arranged in this way said to be the parallel field. So what he said, the singly maximum extent possible, and the electron in given subshell all have the same spin magnetic quantum number. So now he arranged in a way have parallel spin. For example, can we go for the carbon atom? You have 2p electrons singly occupied. 2 of the 3 2p electrons. So they will be the parallel to each other so that they can have the same spin. So what is his telling? Simply, right? We have done for carbon. Okay. When you want to fill, yes, what is the electron configuration of carbon? 1s2, 2s2, 2p2. So when you go for 1s2, 2s2, 2p2, you will have 3. Okay. Right. According to that, the 1s2 should show the opposite spin. You have to come upward, down. 2s2 also upward, down. And 2p2, you could not fill like this. That is wrong. Why? It has the same energy. So first it should be what? The singly filled. That's what the concept is saying. So you should write this. This is very important. This is what you have to understand under this. Right? Okay. So clear or drop. So this diagram, the distribution of the some elements in the second and third period is given. So go through here. When you go for neon, right? So when you take the neon, you can have a look, right? Yes, this is what the first orbital. Okay, that is correct. This is correct. And it should have the 2p6. That is also correct. And go for the boron, right? What is the total electron should be present? 5. So you have 1s2, 2s2, 2p1. Can you see? This is how you have to. And again, sodium, right? You have to go like this. And go for the nitrogen. Yes, 1s2, 2s2 is okay. The 2p3, that means you have to fill like that. So after nitrogen, you can go for the oxygen. So the oxygen will come like that. Yes. 1s2, 2s2, yes, 2p3, right? I will show you that one here. Lol. When you do like this, yes. This is for 1s2, yes. And this is for 2s2, yes. So 2p, we have 3, that is 1, 2, 3, and again 4. This is what the difference. You have to understand how I have done this, right? So this is for what? Who's that person? Oxygen having 8 electrons. Clear? Hopefully, guys, go through. There are some exercise. If you start right, you will be familiar about that. So next we will go for what? The condensed electron configuration. Actually, we have until now we studied how to write the electron configuration according to your subshell and orbitals and electron filling order. How this is filling the singly and that the same orbitals. The same orbitals containing the electrons should have the same energy. So that should be the parallel string should be there. This is what until now we have studied. And now we have the different type of the writing electron configuration. So this is what the electron configuration of sodium atom, if you know that is 11, you can written as like this, that is 1s2, 2s2, 2p6, 3s1, where the 2p subshell is complete like neon. So which has stable configuration with 8 electrons and octet in the outermost occupied state. So what they are telling under the condensed electron configuration, whenever you want to write any atomic numbers, right? According to the electron configuration, we are taking the noble gas, whatever having the fulfilled configuration, and you can write it like this. This is what the sodium marks the beginnings of the new row of the periodic table, and therefore we can write the electron configuration of sodium is neon 3s1. Let's see where we will have an idea, guys. When you take the neon, that is what? Yes, we already said you will have the neon is 1s2, 2s2, 2p6, yes, not 3. So this is for neon. Okay. If it for the sodium, what is that? Same thing. 1s2, 2s2, 2p6, and 3s1. And this you can write as like, clearly you can see here, that is neon in between the square bracket and the 3s1. This is what the way of writing. Okay, guys, so we will have the clear that by having the one. Okay, so the part represented by the brackets. So this noble gas we are calling the core of the atom. These inner shell electrons are referred as the core electrons. What? Represented by the neon. The 10 electrons we are telling as the core electrons. The electrons given after the noble gas core are called as outer shell electrons or valence electrons. You should be very clear about that. So when you take the sodium, right, you can write the sodium as what? Neon within the square bracket. And next, 3, 3s1. And this is what we are telling is co-shell. So this is, you can say, co-electron having chain. And this is, we are telling as what? The valency electron. So the sodium having 1. So this is the difference. This is what they are trying to teach me all. The outer shell electron include the electrons involved in the chemical bonding as they are called as a valence electron. We already studied, right? Your outer shell containing the electron will involve the chemical bond. So example, when you take the phosphorus that is 15, you can represent as what? 1s to 2s to 2p6, 3s to 3p3. But this is what up to this, you can see here. Up to here, it's a stable configuration like your neon. So you can write the neon within square bracket and 3s to 3p3. And this is what we are telling the valency shell electron, valency shell electrons. And these will go for what? The bonding manner, right? So likewise, we can assume all noble gas to write the condensed electron configuration. This is the examples. The manganese, when you take the manganese, right, this is how you are writing the electron configuration, and zinc, right? So what is the atomic number for manganese? That is 25. What is for atomic number is 30. According to that, we have select the maximum filled electron one. The manganese before that, you can see the noble gas, the maximum filled electron is 18, right? When you go for the zinc, there should be full. Again, it's 18, the noble gas selector. Then you can write clearly, you no need to write the full electronic configuration, and the rest part, only the valence electron you have to draw as an orbital diagram. And there is now we are going to speak about what the elements with complete or precisely half-filled sub-energy level. That should be appear to be relatively more stable than the elements with other electron configuration. Here I am going to speak about what? The electrons with what? The fully filled one or precisely half-filled sub-energy levels. So that should contain the very stable configuration. According to that, the elements with the configuration ending with S2, P6, D10 will be more stable. Right? Take your zinc, you have what? The argon 3D10 4S2. If you take the magnesium, that is neon 3S2. Argon, yes, neon 3S2 3P6. Nitrogen, you can go for the helium 2S2 2P3. And your manganese, you can go for what? 3D5 4S2. Will be the relatively stable atoms. Right? Why? The elements configuration ending with the S2P6D10 resembles the stable configuration, stable atom. So these electron configuration of certain elements deviate from this Bose configuration as we discussed until now. Yes, what happened? The electron configuration of the chromium is element 24. It should have the argon 3D5 4s rather than 3D4 4s2, which we might expect. As well as like your copper element having the 29, that should be argon 3D10 4s1 instead of having what? The argon 3D5 4s2. What they actually is. When you take the chromium, right? You have the chromium, right? What is the electron configuration? Yes, the chromium is, as they said, it's a 24. So you have argon, right? You will have 3D4 4s2. So here, rather than having like this, you have to write this is as argon 3d5. OS1. So this is very clear, guys. So when you go, what we expect the usual manner is this is what, but this is not for the, according to their stability, the 24. Their stability, this is what expected. And they are taking, right? Okay. When you go for the copper, if the copper is 29, copper, right? When you go for the copper, yes, again that should be have the argon rather than having 3d 9 4s1, it will become as a argon argon 3d 4s. This is what we are not taking this. This is the correct one. This is the major what they are telling. This is what is a kind of the exemption what we study until now, right? Okay. So therefore, what they are telling us, that anomalous behavior is largely a sequence of the closeness of 3D and 4s orbital images. So infrequently occurs when there are enough electrons to form the precisely half field sub-energy level as in a chromium, or completely field sub-energy level as in a copper. It would be relatively stable configuration. Why your 3D and 4s orbital somewhat the not largely sequence, very closeness of the behavior. Therefore, we have derived that is a kind of the exemption about until now what we have studied. You should be very careful when you are writing the proper formula. So according to that, I am going to complete my presentation. I'm going to say right after my presentation, guys. Thank you very much. We have studied the very important and very useful stuff that you are going to use here after how to write and precisely preparation. See you on next presentation. Until that, guys, see you. Bye bye. Assalamu alaikum wa rahmatullahi wa barakatuh.